And the radiations that were emitted, to make a long story short, were 3 different types. Now, you might think they'd call them maybe A, B, C, right? But these are physicers, gang. We didn't call them A, B, C. You know what we called them? Alpha, beta, gamma. That's A, B, C in Greek, yeah? So alpha, beta, gamma rays. And it turns out that those radiations, you can find out there's 3 different types of radiation by simply getting a lead block, boring a hole in it down to about the center, and then putting in some radioactive substances. These are heavy minerals. And it turns out these radiations will be emitted in all directions, but the ones coming out here will comprise a beam. And then in that beam, if you put a magnet, it turns out that in that magnetic field, the beams will separate. Some will. Some will just keep right on going. And some will bend this way, and some will bend that way. And if you had a piece of photographic film out here, you could catch splotches here, here, and here. 3 distinct splotches, which would indicate there are 3 different kinds of rays coming out. We call one the alpha ray, we call the other the beta ray, and we call the one that's undeflected the gamma ray. So alpha rays are charged one way, and beta rays are charged the opposite. Opposite charged rays. So these rays were comprised of particles with electric charges. To make a long story short, the alpha particle turned out to be, the alpha radiation turned out to be the nucleus, the nuclei of helium atoms. And it turns out that the beta particles were electrons. Just plain old electrons like that which flows in an electrical circuit. And it turns out that the gamma, alpha, beta, gamma, is just your E and M radiation. Doesn't have any charge, just like light ray doesn't have any charge. It's just pure energy. Pure energy of electromagnetic fields, okay? And your beta particles, just electrons. And your alpha, helium nuclei. Now those helium nuclei, an alpha particle and a beta particle brought to rest will make up what's called a helium atom. Because this is the nucleus, this is the orbiting electron. And so the next time you see a kid walking by with a balloon filled with helium, tell the kid's mother, hey, kid, you know what's in that balloon? And just tell the mother, that's radioactive debris from uranium and radium and dangerous things like that. True or false? That's true. That's true. But these particles now have lost their energy. If you walk by an old historic site and you see an old cannon, and you see some of these cannonballs all sitting, all piled up, do you get scared when you walk by those cannonballs? You don't get scared when you walk by those cannonballs. They have no more energy. Not the energy they had when they were projectiles in some war or something. So just as those cannonballs are not dangerous anymore, the alpha particles that in the beta particles that make up helium gas in a balloon is not dangerous. They've lost their energy. This piece of chalk isn't dangerous, but if I put this piece of chalk in a shotgun and fire it at you, then it is. And that's the difference between the particles that are ejected from the nucleus. They come at very, very high speeds. High speeds, a lot of energy. They can tear into you, and then maybe that's not so good. But once stopped, they're completely harmless.